Hey guys, welcome back to the Dynamics video series. This is the first video after spring break. I hope you had a good one. This video is going to be covering vector loops and how we use them for these problems where we have rotating bodies that are linked or connected in some way. This is my third time recording this video because the other two times got corrupted and I couldn't use the file. So if you're seeing this, I really hope it records and I really hope you see it. But nonetheless, let's get into it. So the diagram shows two links, a black and a red one. The red dot is attached to the red link and slides inside the black slot. Coefficients of friction are 0.3, 0.4 apparently, and the link has a mass of 2 kg each. Gravity points towards the bottom of this page. L is 0.5 meters. D is 0.6. I'm just going to fill that in straight away. So this is 0.5 meter, and then this over here is 0.6. Easy peasy. Links have a mass of 2 kg each. Oh, I already read that. Determine the angular velocity of the black link if the red link is rotating at 10 radians per second counterclockwise, right? So counterclockwise is in this direction, right? So it's rotating this way at 10 rad per sec. Okay, so let's keep going. So we can start by creating our loop. First thing I'm going to do before we create our loop is I'm going to label these angles. So these angles are currently 30, right, at this snapshot in time that we have, but they're not always 30, right? They do change because these things are rotating, right? So relative to the horizontal, these black and red links are changing angle, right? So let's just label it as some variable. I'm going to call this angle theta. I'm going to call this other angle beta, right? Easy peasy so far. So let's start by creating our loop. So I'm going to start at any of these points. Let's just pick this one, just to go from left to right or something. But before I do that, last thing before I do that, let's initiate these I and J components, right? So if you don't remember, these are the I and J unit vectors, right? They basically represent an X and a Y, like unit direction as a vector. And they're going to be really useful for these vector loop problems and for the special points problems that we're going to talk about in the next video and in your next lecture, I'm sure. But forward, just keep those in mind for now. So that's going to be our axes. So as we move, right, let's say we're going to create a loop, vector loop, haha. We're going to initially create our first portion as from this point over here to the actual point of interest we're talking about, right? And we want to figure out what are these distances, right? So I have a horizontal and I have a vertical distance, right? So this bottom part is just going to be the cosine of this angle, or cosine of theta. And then this vertical part is going to be the sine of this angle theta, right? And this is in the going up, so it's plus j, not y, j. And then this is going to the right, so that's plus I, right? And then, so that's our first part, so let's write it out. So that's going to be L multiplied times these two things, right? So L, the cosine of theta, plus the sine of theta. Oh, let me not forget what I just said about my I and my J components. So it's cosine theta in the I, plus my sine component in the J. Okay, perfect. So that's that part. Let's continue making our loop. So then we're going to go down here. Okay, and then what are these components, right? So as I go down here and across here, what are these components? So this bottom part is, again, the cosine of, now it's beta. And then this vertical portion is the sine of beta. Okay. So let's add that. So I'm going to add, and then this is going to be this distance d times these two horizontal and vertical components. So the horizontal component is cosine of beta. So if I imagine myself walking on this little thing, right, where I'm going across it, right, this is me, and I'm going this way. Horizontally, I do have a horizontal vector. It's positive, right, because I'm going to the right, and I said to the right is the positive I. So this is still positive, and that's the cosine of beta, right? And then now I have a, that's the I. I have a J component, and then for the J, I'm actually going down, right? So this is actually a negative sine of beta in the J. Cool. All right, that's that. So now we have this last portion, or these last two portions, where we have this horizontal component and this vertical component to get back to where we started. So if you notice something, both of these components, right, this to this, both of these little things that we're standing on or that our rods are connected to are fixed points, right? So they have no relative velocity. Sorry, relative like change in position with respect to each other, right? They're stationary. So this horizontal distance is just going to be a constant value. We can just call it x. And then this vertical distance that we go up is just going to be y. Right? We can just label that as two arbitrary constants. We can solve for what they are, but the numbers don't really matter because we're not going to need them in any way to, to solve this, right? Because we're going to be taking derivatives with these vector loops. But I'm going to add them just to keep it consistent. So I'm moving to the left in the horizontal, so that's minus x in the I. And I'm moving up that y distance, so that's plus y in the j, right? And now I have my full vector loop, right? So now this full vector loop is complete. Since I ended up exactly where I started, that means the sum of all these vectors is going to be equal to 0. Right? So all these vectors sum up to 0. Perfect. Now what we can do is start taking derivatives. Real quick, let's point something out, right? So this my L, right? I left it as L, right? And I didn't replace it as its value because the L value is changing, right? Because you can tell that as this thing slides in and out of this slot, right? Or not in and out, but just in one direction. Maybe it's probably going to go this way. That this L value is going to change, right? Or the distance between this fixed point and this intersection point is going to be different. But that is not the case for the red, right? For the red, this dot is stuck to it at a certain point. So it's stuck here, and this d distance is going to be a constant value, right? So I can actually just replace this d as its constant multiple. So this becomes just 0.6 constant multiple. And now I can do a derivative, right? That's easier. So I like writing the Mathematica like derivative command or function. Just to remind myself I'm taking a derivative. So let's do it. So as I take a derivative, I'm going to start from left to right. So let's see. So I have L, right, which the length we said was a function of time, right, because that thing's changing. And theta is also going to be a function of time. So when I take these derivatives with respect to time, I also just realized I input theta here. Let me scoot this over. Yeah, there's supposed to be a theta here. Good catch if you got it. Did I do the rest right? Yeah. I actually have to use the chain rule when I do this, right? Because I have something multiplying something else, right? That are both, neither of them are constants. They're dependent on time. So how does chain rule work? Or not chain rule, product rule. It's the first one times the derivative of the second. So I'm just going to leave L as is. And then the derivative of this second term, right? So derivative of cosine theta is negative sine theta. And then we got to use our chain rule. This is going to be times the theta dot, right? Or that time derivative of theta. And then derivative of sine is cosine, so just plus cosine here. Theta, and then theta dot. And then again, don't forget that these are in the I and in the J respectively. All right, and then I do my second part of my product rule, right? So where I get the derivative of that first term. So the derivative of L with respect to time is just L dot. And then copy my second term, right? So I'm just going to copy cosine of theta in the I plus sine of theta in J. Perfect, and that's that term. The next term, I'm going to do the term with the 0.6, take the derivative of that. When I do that, that constant multiple stays as is, so 0.6 times, and then the derivative of whatever is in that parentheses, right? So again, derivative of cosine is negative sine, so I'm going to do negative sine of beta times beta dot. Cool. And then that's in the I component. And then minus sine, so derivative of sine is cosine, so this is still minus cosine of beta in the beta dot, not in the, but times beta dot in the j direction. And then my x, right, and my y that I wrote here for the I and the j, I said that they were constants, right? And so when we take the derivative of a constant, they just disappear. So I'm just going to like scribble over them to show them gone. Because they're going to disappear as I take this derivative. So my derivative is done. it's at this point that I can start doing separation, right? So I'm going to separate these into their I and j components, right? We said this whole thing is equal to 0, right? Or the last equation is equal to 0. The derivative of a 0 is still 0, right? So this equation is still equal to 0. And since it's equal to 0, and then I and j are orthogonal to each other, right? So they don't contribute to each other at all. We know that the summation of all the I terms and the summation of all the j terms is also equal to 0, right? So I sum is equal to 0. The j sums are all equal to 0. So I'm going to create my I and j little equations, or my summations of all the I terms and all the j terms, right? So I and j are here. So my I term, I'm going to go ahead and distribute all my coefficients that I have, right? So I can do all this to all of them. So I'm going to do that as I go across. So the first one is going to be L times negative sine. So this is going to be negative L sine of theta times theta dot. And then I know it's in the i's, right? So I'm going to leave out that next j term, and then so it's plus that L dot term. So L dot times the cosine of theta, right? And then I'm going to move over to that 0.6 term. So then this is 0.6 times negative sine. So that's negative 0.6 times the sine of beta times beta dot, right? And then that last part is in the j, so I don't need it. So that's my full I component. My j component, I'm just going to do the same thing, but for the j's. So this becomes, I'm just going to write it out, L cosine of theta times theta dot plus L dot, and that's the sine of theta. And then minus, again, minus 0.6, and that's the cosine of beta times beta dot. Right. So I have these two equations, and I have a bunch of variables in them. Both of these are equal to 0, like we said earlier. Right? So let's see, what do I actually know, right? So I can figure out what variables I need to solve for. So I know my beta, right? It was given as 30. And this is also equal to my theta, right? So theta and beta are both 30. I also know my L, right? At this moment in time, even though we said it's changing, at this moment it's 0.5, right? So we can use that. And I know my beta dot, right? Because it told me my angular velocity of this red thing, which is related to that beta angle, right? So if this thing is changing, right, it told me the beta dot is 10, right? So beta dot is 10. But is this angle getting bigger or is it getting smaller as time goes, right? So since this thing is rotating, unhighlight, counterclockwise, right, or in this direction, you can see that this angle would be getting smaller, right, as time passes, right? So this is going to be a negative 10 radians per second. Okay, so I have all these values. Let me see what I know versus what I don't know. So I know L, I know theta, I know beta, and I know beta dot, and I don't know theta dot, I don't know L dot. All right. So I have two unknowns and two equations. Perfect. All right. So now we can rewrite this and then use algebra. So let's go ahead and rewrite it. So I have that negative L, which is negative 0.5, times the sine of 30, not 3 theta, 30, theta dot, plus the L dots times the cosine of 30, minus 0.6 sine of beta, which is 30, times beta dot, which we said was negative 10, and that equals 0. And I have this other equation, 0.5 times the cosine of 30 times theta dot plus, is it plus? Yeah, plus L dot times the sine of 30. And then a minus again, 0.6 times, now it's the cosine of 30. And then times negative 10. All right. And that all equals 0, right? So again, I have these two equations for these two variables, right? So I can solve this, and I get that in my final answer when you solve it using whatever method you use, whether it's Mathematica, MATLAB, doing it by hand, calculator. When you do this algebra, you get that theta is, or theta dot, I should say, is -6. Well, what does that mean, right? So that means that this angle should be getting smaller. So if it's getting smaller, it's rotating in this direction, right? Which is the clockwise direction. So what this means is that this thing is 6 rad per second, or radians per second, clockwise, right? And that's going to be our final answer. I really hope this video recorded. I'm tired of recording it over. But that's the essence of these problems, right? So make sure you're using your vector loop correctly. You're going from point to point, making sure you're keeping track of what stays constant and what changes, right? So leave as a variable everything that changes, like angles, these L distances. Keep track of what remains constant, so like X, Y, and D in this case. That's kind of the essence of these problems. Make sure you're good at taking these derivatives, right? So whether you use Mathematica or you do the chain rule and product rule stuff by hand, both strategies work, just whichever you're more comfortable with, and just get used to your I and J components. But that's going to be the end of this video.